Imagine that your task is to open a jar. To do this, you need to apply the force to the jar properly, synchronized with your hand motion. Now you want to teach a robot how to perform this task. In this case, only retargeting the motion would not be enough. To achieve the goal, a robot also needs to learn when and how to adapt its endpoint stiffness. To do this, existing works usually rely on special devices such as SEMG sensor or grip force sensor. However, this makes the whole framework hard to use, less accessible, and less generalizable. To overcome this issue, we propose a vision-based tele-impedance system, which relies on an affordable webcam. This enables us to build easy-to-use, accessible, and generalizable tele-impedance control system. Our main task is pushing an emergency button that requires enough force to be successfully pressed. First, our vision-based tele-impedance system estimates the human pose. Based on the estimated pose, an image patch is cropped near the target muscle region. After collecting a set of target muscle image patches, it is used as an input for the muscle activation pattern estimator. This estimator results in a static state, which shows whether the muscle is activated or not, and a temporal state, which shows whether the degree of activation is increasing, stable, or decreasing. Based on this information, a robot adapts its endpoint stiffness properly to successfully conduct the task. The proposed muscle activation pattern estimator, which we call MAPE, takes a series of image patches as inputs, and these image patches are the ones observing a target muscle. Then, we extract features from images based on the ResNet. The sequence of image features is processed with LSTM recurrent neural network. Finally, the last hidden state from LSTM is used to classify as static, as well as a temporal state. However, a vanilla MAPE has low generalization performance. It is because the visual traits of human muscle are different from individuals, and the collected dataset cannot handle every situation or environment. To overcome this issue, we propose additional processes such as data augmentation and visual calibration. To overcome the limitation in the collected dataset, we use several data augmentation tricks. First, images are randomly rotated, translated, and flipped. Second, brightness and contrast of images are randomly changed. Finally, a background is randomly changed, so that the trained model can be robust to various environments. Visual calibration reduces the effect of individual muscles' visual traits. To do this, a human records a muscle image when it is activated or inactivated. Then, relevant image features are extracted. Afterward, when new inputs are received, the model generates calibrated image features by considering the activated and inactivated muscle images. The sequence of calibrated image features are given to the LSTM recurrent neural network, and its final hidden state is used to obtain classification score for static and temporal state. Results clearly show that the muscle activation pattern estimator works much better when data augmentation and visual calibration are applied. For detailed qualitative as well as quantitative results, please refer to our main manuscript. For our real demonstration, we transfer the estimated static and temporal states of muscle activation patterns to the robot. To command the robot's end effector stiffness, we designed a finite state machine that acts on the incoming state estimation while also filtering out possible noisy states predicted by our model. Based on the internal state of the finite state machine, the Cartesian robot stiffness in the direction of motion is set. Thanks for your attention. For more information, please refer to our contact information. This audio was generated by Clova.